All right, let's talk penguins here. We have four masses. We're calling them penguins. I've abstracted them out here into just rectangles, being playfully pulled, so they're having fun, all right, along a very slippery, frictionless ice by a curator. This is also horizontal. So, frictionless, horizontal interfaces here. We are given the masses of three of the penguins, and we're given the tension in two of the chords. And what we're being asked to determine is the penguin mass that's not given. So we're going to have to go through and analyze these four bodies. So in order to do that, I'm going to name some of the unknown things that I'm going to need here. So the unknown penguin mass, I'm going to need to call it something in my work. So I'm just going to call that capital M. I'm going to go back to my pen and call that capital M. And then there are two tensions that aren't given. I'm going to need to call those something because when I draw the free body diagrams for each of the penguins, I'm going to care about what those tensions are. So the unknown tensions, I'll call this one here T1, and I'll call this one over here T2. And we're given the tensions T and 2T as shown there. Okay, so what we need to do then is consider a free body diagram for each of these penguins. So I'm going to let me name the penguins actually. And just for ease of reference, then I'll name them Penguin A, Penguin B, C, and D. All right. And I know, well, I want you to think about this for a second. Let me ask you the question. Are the penguins accelerating? So you can pause the video right now and consider this if this feels non trivial. Um, and we know that they are accelerating. The reason is that if the curator is pulling these penguins to the right with some non-zero force, that force 2t there, and we're told that the surface is horizontal and frictionless, then there's no force towards the left, right? There's no, if I consider all the penguins together, there's no leftward force. Another way to think about this, as far as like, is the situation accelerating? Are the penguins accelerating or not? Now, the simplest penguin, the simplest case here, notice, is penguin A. So just like kind of look at penguin A here for a second. And that one is the simplest because there's really only that one force of tension on it, right? Which is pulling it to the right. So if you look at that penguin and consider the free body diagram for just that penguin, you can see that that penguin must be accelerating to the right. And since they're all traveling together, they all are accelerating to the right. Okay, we'll see that a little bit more once we get the free body diagrams out here. So my acceleration, I have acceleration directed to the right in this case. So let's launch into our free body diagrams here. Um, and everything else comes from that. Free body diagram for penguin A. Now, there is weight and normal force on this penguin. There's no acceleration at all in the vertical, so I know the vertical components sum to zero. I can place them on here. I'm not going to be using them in my analysis at all. I'll put them on here though. So we have the weight of penguin A. I'll call that weight A. And then upward, we have the normal force on penguin A. Again, those are equal and opposite. There's no acceleration in the vertical. The action here is happening in the horizontal. So horizontally, I'm going to switch up colors because this is the force we're using for analysis here. Horizontally, I know that to the right on this penguin, I've got tension T1. Okay. And those are the only forces on the penguin. Remember, you have one invisible force, which is the weight. Every other force must be exerted through contact. What's contacting penguin A? The surface beneath it and the string attached to it. And we've considered both of those. The surface exerts a normal force, the string exerts a tension force. So done with that penguin. Penguin B, same thing. Again, we draw one free body diagram per body here. So penguin B, again, I have its weight, the weight of penguin B, and the normal force on penguin B. I have to subscript those because the weights, if I just put W for weight on all the penguins, they're all different, right? So in science, when we use a symbol, it means something. If I use the same symbol for all the weights, that would be me representing that all the weights are the same. That's not correct because they're not. So I have to subscript those here. So now I'm going to consider the horizontal forces. Those are the ones that we're going to be actually analyzing. For penguin B, we have the tension T to the right, and then we have the tension T1 to the left. And that's it. Those are what's touching penguin B, the surface beneath it, and the two chords. And then we have our one invisible force for B, which is weight. Then we'll look at penguin C. Do the same thing. We have the weight of penguin C and normal force of penguin C. I know those are equal and opposite due to the fact that acceleration is 0 in the vertical. And the forces, horizontal forces, I have T2 to the right and T to the left. And don't get too caught up at this moment in what you know or don't know, what's given or not given, because you're going to generate a whole bunch of equations. Remember, you're going to generate one equation per penguin in this problem. So we don't expect to have the answer right in front of us. Free body diagram for penguin D. Do the same thing. I have weight of penguin D, normal force of penguin D. And then for D, I've got 2T to the right and then T2 to the left. All right. So I've taken care of all my forces. Now I need to put a free body, or sorry, a sign convention on this so I can start summing them up. These are vector diagrams, of course. Forces are vector quantities. And so in order to um, negotiate dealing with those vectors, I need to come up with some kind of sign convention. So I'm going to do that for this problem. I would choose um, upward positive and I'll choose rightward positive. We're not going to use the vertical, but for I don't know, completeness, I'll do a two-dimensional sign convention. Just a little note there that often, if you know the direction of acceleration, like in this case here, you know that acceleration's to the right, it is often beneficial to choose the direction of acceleration as your positive direction in force analysis problems. I'm going to say that one more time. If you know the direction of acceleration in a problem, it is often beneficial to choose the direction of acceleration as positive. And that it just decreases errors when you're applying Newton's second law here. So rightward is positive and upward is positive. I'm just going to add that really quick to all of my free body diagrams. It helps to have your signs right in front of you when your brain's looking at the diagrams. So now I'll go ahead and apply second law. Newton's second law tells us that the sum of forces on a body is equal to that body's mass multiplied by its acceleration. So Newton's second law is very much a cause and effect relationship. Forces cause accelerations. When you're interpreting this equation, it looks pretty little and cute and manageable, but the meaning is pretty huge. Again, consider it to be that forces cause accelerations. Accelerations don't just happen, accelerations are not exerted. Forces are exerted, and those forces cause changes in velocity. And a change in velocity is something that we describe as an acceleration and calculate as an acceleration in physics. Okay, so applying second law, then I'm just going to apply it in the horizontal again and I'll do this one free body diagram at a time. So if I'm looking at free body diagram A here, I will say again, rightward positive. So forces to the right is just T1, set that equal to the mass of A, which is M, given as M in this problem, multiplied by the acceleration of that block. That's all I can do there for case A. Now let me look at penguin B. Now I have two forces on it. I have T going to the right, which is positive, minus T1, which is directed to the left, so it's negative. That's it. That's all I have in the horizontal. equals to the mass of penguin B, which is capital M, multiplied by A. I'm going to use the same A here because all four penguins move together. So their acceleration will be the same. I don't need to subscript their accelerations. They're all going to move together. They're all going to have the same acceleration. Free body diagram for C. T2 is tension to the right, so it's positive, minus T1 is to the left, equals the mass of penguin C, which is 2m, multiplied by A, that same acceleration we're working with. And then finally for penguin D, 2t, that's to the right, minus T sub 2, directed to the left, is equal to the mass of penguin D, which is 3m, multiplied by acceleration A. Now notice that the right-hand side of each of these equations that I just wrote out here, right? These are my Newton's second law equations. Notice that the right-hand side is positive in all these cases. These are vector equations. The directions matter, the signs matter. They're positive in each case because we chose positive in the direction of acceleration. So had you made a different choice for coordinate system, it's true that coordinate system choice is arbitrary. You can do what you want. But you have to make sure that your coordinate system choice is represented in your math at the same time. So had you chosen left positive, your signs would be opposite in all of these equations. Okay, just wanting to provide a little motivation there. So now I can start doing some algebra. Notice that I have four equations, and let's consider our unknowns here for a moment. What are our unknowns? So what don't we know? We don't know that mass of the penguin that's being asked for. We don't know this T1, the tension that we is not given. T2, there's another tension not given, and we don't know the acceleration. So we have four unknowns, and then conveniently we have four equations. So that makes us happy. I think it's always a good idea after you've rendered your equations to count unknowns and count equations and make sure that you're not just going to be wasting your time going in circles. If you have four unknowns and three equations, I don't care how good your algebra is, you're not going to be able to solve it. You just simply don't have enough information yet. So do that little bit of math, pause. How many unknowns do I have? How many equations do I have? And then the rest is algebra. So your physics is pretty much done at this point. You can put these equations together in whatever way you want, simultaneous equations, substitution. In the written solution here, I use substitution, but algebra is personal also, so use what makes sense to you there. The final result here that we get for the penguin mass that we don't know is equal to 4m.